Hello everyone, my name is Umair. I'm a developer at LoyaltyOne, and today I wanted to talk to you guys about our journey deploying clustered Akka applications on Amazon ECS. So if you're not familiar with Akka Cluster, it's a way to build distributed, fault-tolerant applications that scale to multiple machines. And we'll get into more details about these systems in a bit. I just wanted to cover a little bit of a background on our motivation for deploying these on this platform. So recently at LoyaltyOne, we decided to deploy most of our new applications to use Docker, and we wanted to containerize these applications and deploy them to Amazon. So Amazon provides this platform called ECS, which is the EC2 Container Service, and it makes it very easy to run these containerized applications for us. So our team recently, we started to build our applications with Akka Cluster, and we wanted to use this same platform for our deployment. So we decided to deploy our clustered Akka application on Amazon ECS. So what we'll do is we'll go through some of the basics of ECS first, then we'll cover a little bit of what Akka Cluster is, and then we'll cover some of the challenges associated with deploying these applications on ECS. So what exactly is ECS? So ECS is really just a service provided by Amazon that allows you to deploy your containerized applications without having to worry about the underlying infrastructure that they run on. So you as the developer can package your application as a container and run it on this platform without worrying too much about these underlying details of it. So you may have heard of other platforms like Kubernetes, Docker Swarm, Apache Mesos. These are all very similar platforms. The basic idea is that they allow you to run your containers in an easy-to-use manner via API calls, and you don't have to worry about the underlying machinery. So I just want to go through a couple of the basic components of ECS to get some context for our deployment. So first, what we have is the container instance. So a container instance is really just a machine that has Docker installed on it, and it has this component called the ECS agent installed on it. So what the role of the agent is to take commands from Amazon ECS. So if you tell ECS you want to deploy a container, it in turn tells this ECS agent, and the agent goes and runs that container on this machine. So together, these container instances, they form what we call an ECS cluster. So a cluster is just a collection of these machines, and the idea is that when you tell Amazon to run your container, it talks to these agents. It figures out where best to run that container based off of available resources, and then it tells one of them to run your container. So how do we tell Amazon how to run our containers? Well, they've provided this mechanism called the task definition, and it's really a way to supply things like the port mappings for your application, the environment variables that you want to supply when it runs. It also allows you to specify the Docker image that you want to run your application with, and constrain your application to certain memory requirements. So if you're familiar with the Docker run command, it's very similar to that. It's really just a way to declaratively describe how to run your containers. So once you provide a task definition to ECS, what it does is it instantiates this thing called a task. And a task is just a logical representation of your running container. So to you, really, a task just runs on this cluster, and you don't have to worry about the machine that it runs on. So tasks by themselves don't really give us a lot of functionality when it comes to running long-lived applications. So, for example, if a task dies, it doesn't come back up. We can't specify a number of tasks to keep alive. So if we want to maintain some sort of availability of our services, there's no way to specify to have a fixed number of these tasks running at all times. So what Amazon does is they have this other component called a service. And the purpose of this service is to maintain a desired number of tasks at all times. So if you want to run your service, if you want to run your application with, like, say, 3 instances, you can do so with a service. And if one of those instances dies, it'll make sure that it spawns up a new one. The other thing it does for us is it allows you to register your containers under a load balancer. So if you have multiple instances of your container, you can direct traffic to any of those instances. Another powerful feature of it is to auto-scale your container. So we're used to doing auto-scaling at the machine level. We can also do it at these container levels. So if you get a lot of load, you can increase the amount of instances of your application. So how do all these components fit together? So we covered what a container instance is and what an overall ECS cluster is, which is just a collection of these instances. And really the idea behind a lot of these platforms like ECS and Kubernetes is to abstract away these details. So you don't need to know about these agents or Docker running or which container is running on which instance. Ultimately, you just want to run your containers, and ECS provides a mechanism via tasks to do that. So for you, you just care about where your tasks, you just care about running your tasks, and as long as they're running, you're happy. So ultimately, you don't care where they run in the cluster. And then Amazon provides that concept of a service to make sure that you have a set number of tasks running at all times to maintain some sort of availability of your service. So now that we have a basic understanding of ECS, I just wanted to cover a little bit about clustered Akka applications. So if you're familiar with an actor system, Akka Cluster is a way to scale your actor system to multiple machines. So the idea is that you have several machines, each of them running an Akka cluster, an actor system. And together, these actor systems communicate together to behave like one large actor system. So what that gives you is the ability to send messages to actors that may live on your local machine or on one of these nodes in the cluster. So to you, in terms of the programming interface, it's the same thing. You're sending a message, and that actor could live anywhere in this cluster. And we'll see how this becomes a pretty powerful mechanism. So we have a basic idea of what a cluster is. So what exactly are they good for? So as I mentioned, they let you send messages without worrying about where the actor actually lives. So it could be living on the machine that you're sending the call from or on a different machine in the cluster. So 2 common functionalities that it supports is, one is to be able to spawn actors across machines in this cluster. So that allows you to overcome the memory constraints or the CPU constraints of one machine and allow you to scale to multiple machines. Another thing it allows you to do is it allows you to take the guarantees you get from a single actor and scale those to multiple machines. So what I mean by that is an actor typically has state, and when you want to modify that state, you have to send messages to it, and they get serialized. And it takes those messages one at a time, and it updates its state. So you're able to maintain a consistency boundary around that state with an actor. And Akka Cluster provides us a way to scale that sort of property across multiple machines. So let's take a look at an example. This is a common example that we see. It's the example of work distribution. So let's say we have a very large file that we need to process, and it consumes a lot of memory that one machine may not have. So we have this 3-node cluster here, and one of the actors running on it is the master. And what happens is a request comes in to process this very large file. And what the master does is, using Akka Cluster, we can spawn worker actors on these other nodes. Nodes that have available resources, we can spawn actors there. So we spawn these worker actors, and what they do when they come up is they talk to the master, they reach out to it, and they ask him for work. So all of them reach out to the master. They're like, hey, I'm available to do work. And then the master, what it does is it could split up this large file and basically tell these workers where in the file they should process. And so it sends back this information to the workers, and they're able to process these parts in the file. And when they're done, they can ask for more work, and eventually you can deplete this entire file and process this large file. And eventually, you can scale this to multiple files, of course. And one thing that was mentioned in the talk as well is these other platforms that are coming out, like Spark and Flink. Spark, I think version 1 used Akka Cluster under the hood to solve a lot of the functionality that you get with this work distribution pattern. So another thing I talked about is this consistency boundary being available across multiple machines. So actors inherently are able to guard their state and only change it via messaging. So in this example, let's take an example of like a movie theater and booking seats in a movie theater. So let's say you have a theater and it has a certain number of seats, and you want to make sure that people can't overbook seats. So what we'll do is we have this 3-node cluster, and each node in the cluster is running an HTTP server. And we launch this actor that has 10 seats available. It represents one movie theater. So people are looking at movies, and they see some movie that they really like, and a bunch of people decide to book the same movie at the same theater. Let's say it's like Blade Runner, everyone's excited. They decide to all get on their computers and book this thing all at once. So what happens is we get 3 requests coming into these nodes at the same time. And then what Akka Cluster does is it's able to route these requests to this one actor living in the entire system. And it's also guaranteeing us that only one instance of this particular movie actor lives in this entire system. So what that allows us to do is it allows us to use the functionality of an actor guarding that internal state. So in this case, the state is 10 seats, and we want to make sure that people can't overbook. So what happens is all of these messages gather up, they get into the actor's mailbox, and it processes them one at a time, making sure that if it didn't have enough seats, that those requests would fail. So it updates its state to 7 after processing those 3 messages. So as you can imagine, if we had a lot of theaters serving a lot of movies, we might not be able to fit all of these actors in one machine. So Akka Cluster allows us to spawn these actors throughout this cluster, use all these machines, and fully utilize all of their resources. So we've seen some of the use cases of Akka Cluster, but how exactly do these clusters form? So how is it that we can add capacity to the cluster and have nodes know about each other? So let's take an example. We have a 4-node cluster. One node in this cluster we've designated as the leader, and he's responsible for managing the adding and removal of nodes into the cluster. Another node we've marked as the seed. So this guy sort of is the designated entry point for people that want to join this cluster. So any node that wants to join this cluster would know the address of this seed node. So we have this node E that comes along, and he wants to join this cluster. So the first thing he does is he sets his own internal state to joining. And then what he does is he reaches out to this seed node because he's the designated contact point. So he tells the seed node, hey, seed node, I want to join the cluster. And the seed node is like, cool, I need to tell everyone else in the cluster that you're joining. So what he does is via this gossip protocol, he propagates this knowledge to the neighboring nodes in the cluster. And they learn about node E joining as well. And eventually this knowledge gets to the leader. And as I mentioned, the leader is responsible for managing the adding and removal of nodes. So what the leader does once everyone knows about this node joining is he tells the node that that node is now a member in the cluster. So once the node's a member in the cluster, he needs to tell everyone else in the node in the cluster that he's a member. So he follows a similar gossip protocol, and he talks to his neighbors, and the leader, since he knows, he also talks to his neighbors, and eventually everyone knows about this node as a member of this cluster. So finally, he's an official member of the cluster. And what this means in our terms is we're able to now use this node and spawn up actors on this node and use it as additional capacity in our cluster. So as you've seen, this process is fairly complex. It's not, if we contrast this to our typical stateless application, so an application that just calls a database and returns back a response, those applications typically don't need to know about each other. Whereas in this case, these nodes all need to know about each other. Even when they launch, they need to know about, say, a seed node address. So this presents a lot of challenges when it comes to deployment. And I'm going to call upon Calvin, and he's going to talk about some of the challenges associated with these deployments.
Thank you. Yeah, so I'm going to talk about the deployment challenges we face trying to get our Akka cluster deployed into ECS. So the first problem is we need to take our nodes and containerize them because ECS only works with Docker containers. The second problem is that in order for the nodes to communicate, you just saw like the nodes constantly communicate and gossip with each other. They need to be addressable on their remoting port, and that's how the communication occurs. And lastly, we need a way to add capacity into the system. And in order to do this, we need to be able to know where that seed node is, that contact point. So this is the third problem. So for the containerization problem, we have SPT native packager, right? So this is an SPT plugin that does most of the heavy lifting for us. If you're using a Scala project, you're usually working with, working in the context of your build SPT, and it's an SPT project. So basically, it's a matter of enabling the plugin. And over here, what we're doing is we're setting the Docker repository to loyalty 1. So basically, what we're going to do is we're going to publish to Docker Hub. So when you want to publish when you want to containerize the application and publish it as a Docker image, you log into Docker Hub, you provide your credentials, and then you run SPT Docker publish. So what this does is this prompts SPT native packager to sort of kick in and start doing all the heavy lifting of containerizing your application, packaging it up as an image, and uploading it to Docker Hub. So that's the containerization problem solved. So the next up is making nodes addressable. So as you know, nodes need to communicate with each other, and in order to do that, they need to be able to be reached, and they need to be able to talk to each other, right? So I'm going to go through a simple scenario where we spawn multiple Docker applications up on one machine, and they need to talk to each other, right? So here's a single physical host. This is running Docker, right? So as you can see here, because it's running Docker, it gets a virtual Docker network, so it gets its own address space. So containers that pop up will actually use this address space. So for example, I said I'm going to spawn up 2 containers. So these 2 containers get IPs in that address space, right? So containers need to talk to each other. So let's just assume right now they know what the advertised seed node is, right? So in this example, node B is that seed node, that contact point. So node A knows to talk to node B, right? So, and node B knows to join itself. So basically the communication occurs and the Docker network doesn't get in our way. So everything is great, right? So now let's move to a more complex scenario. Now we have 2 hosts, 2 physical machines, right? Each of them have their own Docker network. They're independent, and they don't know anything about each other's Docker network. So host A does not know about host B's Docker network, and host B does not know about host A's Docker network. So we're going to spin up the containers, right? 1 in each host, right? And we're going to try and attempt this communication. Again, we're making the assumption that they somehow know the advertised seed node. The problem is over here that it's using the Docker IP for the seed node, right? So when the communication starts to take place, there's no route to host B, right? So it doesn't know about node B living in host B. It doesn't know how to get to that Docker network, right? So this is a problem. So, okay, let's think of some solutions. So maybe if we use the host IP, right? So host B's IP, maybe we could be able to communicate and get to that node B from node A, right? So that's actually the solution, and Akka actually allows us to do this. So if you go, so every Akka application uses this application.conf, so you're allowed to specify hook-on properties, so the Akka remote property. So basically what we can do is we can bind to all interfaces inside our container and use port 2552, but we can advertise to everybody else that we're available on our host IP and our host port, right? So I've left these two as environment variables over here. And basically what I'm going to do for this example is fix the host port and fix the host IP. So we're going to fix the host port to 2552, right? Now we're running in EC2, right? So we're running in AWS. So we have the ability to do this metadata query, and we can get information about our host, right? So the information we're looking for is the host IP. So we're able to get this information via this metadata query API. So we have the host IP and we have the host port. Armed with that, let's try and approach this problem again, right? So again, two physical machines. We're going to spawn up the Docker containers, but this time we're going to use the host IP as the advertise port, not the Docker IP. So in this case, it's actually going to route the connection, right? So so node A is going to actually reach host B, and Docker is going to route the traffic to the container, right? So hooray, we have everything working, right? Connection established. We can the nodes can communicate with each other, right? Is everything okay? Well, recall we fixed that host port to 2552, right? So what happens if you're going to try and run multiple clustered applications in our ECS cluster? So let's say we want to run multiple Akka Cluster applications on one instance. Let's see what happens, right? So we have one instance, right? One physical host, and we're going to try and run two Akka applications on it, right? And remember, we fixed that host port to 2552. So the first application runs, it asks for host port 2552, right? It gets it, it's able to spin up, right? The second application spins up, and it's also asking for host port 2552. But hey, guess what? Application A already took host port 2552, so this doesn't work, right? So the port is already in use. So the way to, you can use manual coordination to solve this problem. So you can be like, hey, I'm using port 2552, don't use port 2552 in your Akka Cluster application. But this is not really good because you're sort of losing the abstraction of the underlying platform. Like as Umair mentioned, you don't care where your applications are running. You just care that they are running somewhere in the cluster, right? You don't want to be concerned about, oh, this particular machine in the cluster has its port used, so I can't run it over here. We don't want that, right? So we want to be able to run clustered applications without port conflicts. So the solution is to bind to a random host port. So ECS allows us to bind our nodes to random host ports. And basically, this is great, but from within the container, from inside the container, Docker doesn't really provide a good mechanism to determine what the host port is, right? So we actually built out a service called Docker Mirror. I'll talk more about this. But essentially, what it allows you to do is it actually knows about all the host port mappings, right? So when a container comes up, we're going to ask for port 0, which is saying ask for a random host port, right? So ECS comes back and gives you 41001 randomly, right? So inside the container, we don't know about this, right? We just know it's a random port. So what happens is we run a little bootstrap script that calls out to Docker Mirror and says, for container port 2552, what is my host port? And Docker Mirror knows this information, so it actually responds with 41001. And now inside the container, we're aware of this host port. So we can start up our Akka application and bind to the correct host port, right? And away we go. So what is Docker Mirror? So it's just a Node.js service, and it returns host-level networking information for your containers. So basically, what this gives you is the ability to essentially look at all the containers running on the host and give you container-specific information, host-to-container port mappings, and things like that. So internally, we mount the socket of the host machine, so we're able to look at all the containers that are running on the host machine. So that's the magic that's happening there. I also want to mention that Docker Mirror is running on every single ECS EC2 container instance. So that's how we're able to call out to Docker Mirror. So we actually solved the addressability problem. So nodes can communicate with each other in the cluster. So the last problem is that we have to tackle is the seed node addressability problem. So I'm sorry, seed node problem. And this comes down to how did node E know to join the seed node? How did it know to find that contact point? So a naive solution would be to probably hard code a list of IPs to start with. But the problem is everything in the cloud is dynamic. Amazon can just come and start taking out your instances, and you can't use that instance anymore. It's gone, right? So let's see a better way to approach this problem. So ConstructR is a library that uses a backend. And basically what it does is it makes the process of seed node discovery easier. So it gives you a central location, well-known location to place your seed nodes. So new nodes can come in, find seed nodes easily, and once they join the cluster, they can actually add themselves as seed nodes, and the seed list can update, and they can become contact points as well. So behind the hood or under the hood, Zookeeper is used as that central location. So I'm sure many of you are familiar with Zookeeper. It's a coordination service, so it's used for things like leader election and synchronization. It's used by Kafka, used by Spark. It's found in many of these big data and fast data tools. It provides discovery and registration, so it allows us to find that list of seed nodes, and it allows us to do the registration once a new node has joined a cluster, right? So it allows it to be contact points. So now that we know about Zookeeper and ConstructR, let's see an example, because this is a bit confusing, right? So we have Zookeeper running, right? So when an Akka application starts up, what it's going to do is actually going to call out to Zookeeper using ConstructR, and it's going to say, hey, Zookeeper, are there any seed nodes in the cluster, right? So Zookeeper is going to be like, nope, there's nothing there because you're the first one, right? So it's going to get it's going to get nothing in the seed nodes. It's going to get an empty list. So what the application says is, okay, I guess I'm the first one. So what I'm going to do is I'm going to form a cluster of one, right? So it's going to join itself, right? And it's going to add itself to Zookeeper, right? So now it's a contact point for other nodes that are joining. So when another application joins, it's going to do the same call out to Zookeeper. It's going to ask for seed nodes, right? And it's going to get a list of one back, right? Which is the initial application. So this application says, oh, there's someone in the cluster. So let me go join them, right? So it's going to update its seed list and make the call out to the application. And now they're going to form a two-node cluster. And once this is done, what it's going to do is it's actually going to go and update those seed nodes again and add itself as a contact point, right? And once it does that, it updates its seed list, and the other application also updated its seed list. So these nodes are constantly communicating with Zookeeper to keep their seed list up to date, so they know about all the contact points in the cluster. So to configure ConstructR, it's just a Scala library. So it consists of two parts, the base library and a backend. So the backend we're using is Zookeeper. It actually also supports console, etcd, and a couple of others. So it's a matter of importing those libraries. And since we're using Zookeeper, we have to point to all the Zookeeper nodes. So Zookeeper is a distributed system itself. So it has multiple nodes. Usually you specify the DNS :port. And if you have multiple nodes, you comma separate them. So we've just covered all the challenges that we faced when trying to deploy this into ECS. So now let's look at actually how to deploy this to ECS, right, now that we've solved all those problems. So the prerequisites are to have an existing Akka cluster and to have an existing Zookeeper cluster. So we've actually open sourced all our work on this. So you can actually spin up an ECS cluster in your existing AWS infrastructure, and the same goes for Zookeeper. With that in mind, let's look at the task definition. So as Umair said, the task definition basically maps to your Docker run command. So this is basically saying, how do I get a Docker container running, right? One instance of the application. So if you notice, we have the image, right? This image is our sample application. That's going to be it's on GitHub, and it contains extensive documentation on all the strategies we use to deploy our Akka cluster to ECS. So you'll notice there are two port mappings, right? There's 8080 and there's 2552. So we've seen 2552. That's the Akka Remoting port. So the 8080 is actually because this is a web application. Umair actually briefly talked about it in the consistency slide, where multiple people were trying to send a request for the movies. So it's actually that application. So it actually serves HTTP traffic on port 8080, so we want to expose that. The next thing we do is supply our Zookeeper nodes. So here we're using DNS names. So this is needed for ConstructR. And lastly, we have this app port. So this is actually used for Docker Mirror. So Docker Mirror is completely aware of the port mappings, both of them. So when you're asking for the host port, it needs to know what the container port is. So in this case, the container port is 2552, so it'll give us the host port for that container mapping. So lastly, we don't want just one application. We've been talking about Akka Cluster and dealing with massive loads, so we want to have multiple nodes in our Akka Cluster. So here, we set a desired count of 3, so that means we want a 3-node Akka Cluster, right? And the other thing that this does is the load balancing, right? Because we serve HTTP traffic, so what we want to do is direct all traffic that comes on port 8080 to the containers, right? So all the containers are running that HTTP server, right? All the Akka nodes are running that HTTP server, so we want we want traffic to be sent to all those containers. So once you have the service definition and once you have the task definition, you're just an API call or a few CLI commands away from deploying to ECS. If you want a super detailed step-by-step guide on exactly how we deploy this to ECS, check out the GitHub project, and you'll find a lot of useful information there with pictures and a lot of detailed information. So to briefly recap, we've covered a lot of material. So we've talked about ECS, we've talked about Akka Cluster, and we talked about all the challenges we faced and how we addressed them, right, to get Akka Cluster deployed into ECS. So I'd like to direct you to a very detailed blog post that Umair has written that covers the process in great detail. We just wanted this to be, to give you some intuition on what we've done, right? So it's mostly diagrams, and it's very diagram heavy. If you want like the really down and dirty details, we highly advise you to take a look at this this blog post. It'll give you links to all the repositories that we used, everything that we've open sourced, and it'll give you step-by-step instructions on how we deploy this. So thank you very much for your time. Thank you for listening, and thank you for coming out. We'll take some questions, and maybe we'll have some answers to your questions.
Protocols and communication for nodes. Is it only using HTTP? Have you ever tried HTTP? Oh, sorry about that. For someone, anyone who couldn't listen to me, sorry. So have you ever tried like HTTPS for the connection for the between all the nodes? Is it only for the HTTP tried?
No, so you can use both HTTPS or HTTP. In our setup right now, what we do is we terminate HTTPS at the load balancer level. Mm-hmm. So the traffic going from the load balancer to the container is not encrypted, but everything coming from outside is encrypted. Okay, so it's not a really strict mode then. We're actually having our own now microservice architecture app, and we are having actually so many timeouts travel happening for each node because each component taking so much time SSL validation, the compute. And while they're going like another component and it timed out because it takes so much computations. Right. So your node is like, I think could be one of the solutions if it is also allowed to connect the HTTPS. So yeah, that's why I raise the questions. Okay,
cool. Are you allowed to expose a little bit about why you choose Akka? Like what use cases? What challenges you make you to pick Akka, and how did you? What the evaluation when you evaluate what other candidates? If you, I mean, not covered in the talk, but if you are allowed to expose a bit, appreciate.
Yeah. So one of the challenges we wanted to deal with is just processing transactions and maintaining, like, let's say you have an example of maintaining an account balance. And as I talked about, we had that consistency challenge. So wanted to be able to do this quickly and be able to scale it. And one of the things Akka provides is that ability to route all those messages to, say, one entity actor, like an account that has a balance. We also use it in conjunction with Akka Persistence. It's another library that allows you to use a storage mechanism. So you can treat all of those messages as like events in a log. And it allows us to use that log to later on produce different views of our data based off of the actions that people do on their accounts. So that's mainly the use case that we're looking at. Yeah.
So you have a backend database for stateful service.
Yeah. So even the actors, they're at least in our system, we use like something like Cassandra or DynamoDB. You can use different storage mechanisms to store the messages in sort of a log type of format. But yeah, we use Cassandra.
Thank you.
Do you have a question? Right behind you.
Basically, I have 3 questions. I will ask one by one. So the first one is about the cross-host communication. So yeah, I think I'm curious why you don't use overlay network. It's because, yeah, I think by this solution, you have to open the port to public, right? So I think if you can use overlay network, then it will be other containers running in the same.
I actually sort of mentioned this. Kubernetes and Docker Swarm actually have support for overlay networks. Amazon ECS doesn't have support for overlay networks. That's why we have to do all this work, right? They did introduce AWS VPC networking. There are limitations around that, right? Because what they do is they essentially attach elastic network interfaces to the tasks, right? And that sort of gives you like host mode networking, so you don't have to do all this stuff. But there are limitations around that because, like for example, I believe a C4 large can only have 3 elastic network interfaces attached, right? So what if you want to run 10 Docker containers on that instance? You can't, right?
Yeah, because I never use ECS, so I don't know. So you are not able to touch the overlay network.
No. So they don't. You use the abstraction of the task definition, and they only expose what they expose. So.
It's weird because you introduced the ECS based on Swarm, right? So the overlay network.
It's not based on Swarm.
No. It's a different container platform.
Yeah, it's just like another competitor or
No.
Like an alternative to.
Okay. Anyway, so the second question is about the service discovery and registration. So you are using Zookeeper, but as my understanding, so the recommendation with is DNS services. So why you use Zookeeper? As you bring another services in the whole architecture, make the So yeah, in Docker network, I mean the recommendation was using DNS service.
Right. So again, if you have available the overlay network mechanism, then you can establish DNS names pointing to particular containers as your seed nodes. But we're not really able to do that that well in ECS.
You mean it's also because you cannot touch the overlay network?
That's right. Yeah.
Okay. And also there's problems with that because, like, I've played around with Docker Swarm, and you have to basically fix you have to declare each seed node as a service, right? So say you have 3 seed nodes, right? You declare each of them as separate services. Now the problem is if there's some split brain activity, which I didn't talk about over here, right? Those 3 nodes can be partitioned off from the cluster, right? So now, like they go down, they come up, right? Like these nodes are still up and form the cluster, right? So the seed nodes form their own cluster, and you end up with a split brain scenario, right? So there's limitations with that approach.
Okay, but it sounds like AWS didn't provide a full function Docker network actually.
Yeah, that's right. So they have defined.
Yeah, weird, but I never use it, so a little bit.
Right. So it is a fairly new platform, but they recently decided to include this AWS VPC network mode that Calvin mentioned.
But if that's why you don't implement your like, I mean, deploy Kubernetes just over ECS, EC2 service, no, use ECS service. ECS service is not a fully function.
So it does provide us the managed service. We don't have to worry about the cluster formation of ECS itself. That's something that you have to concern yourself with when you deploy a Kubernetes cluster.
But I think it's worse. But anyway, yeah, the third question, okay. So and the third question is about the service definition. So the service definition is provided by ECS or is from your?
That's right. That's right.
Oh, okay. Okay. Okay, no problem. Thank you.
Thank you.
So my question was more on if you are running it on an extended period of time, what kind of issues you have seen, what are the monitoring and sort of those kind of mechanisms in cloud and Akka?
Yeah, so running it in AWS, like there's a lot of network partitions that can happen, right? So instances can communicate with each other. So if you're running an Akka cluster in production, you need to ensure that you have a good split brain resolver mechanism. So when network partitions do happen and members of the cluster get partitioned off, you have some way to detect that, right, and take corrective action. So you want to, like, for example, if you're using the keep majority algorithm, right? So if you have a 5-node cluster, 2 nodes get cut off from the 5 nodes, you want to take those 2 nodes down, right? Because what's going to happen otherwise is, you're going to lose your consistency boundary, right? Like, you don't want to have that actor, like that single actor that's supposed to be in the entire cluster appear in 2 places, because then it'll write to the database and it'll corrupt the state, right? So that's one problem. Regarding monitoring, we use some cinnamon, like Lightpen cinnamon, and there's also Kmon, which is really great. Yeah, and we combine that with New Relic. Like Kmon has a bunch of backends, so you can use New Relic, you can use Datadog. Datadog's actually pretty good. But the thing with all these tools is you have to like go in and like really tell Kmon, for example, or Cinnamon, like I need to monitor this specific thing, right? So if you forget to monitor something, it won't be monitored, and then you'll have an issue. You won't know what it is, so you'd have to like sort of figure it out. Yeah. So that's another thing.
Thank you.
Oh, sure.
Okay, to ask, how do you guys handle AWS outage? The region is down or the whole data center is down?
So we can handle like data center level because we're multiple AZ, but currently we haven't deployed to multiple regions yet. That's something that we're working on. But yeah, so really at this point, if a region goes down, then our service goes down as well.
So just to build on that, Akka recently had I think 2.5 release. So they started doing the multi-DC Akka cluster. So you can actually run an Akka cluster across multiple regions. And what it does, it sort of like replicates the cluster in this region over here. So in case this goes down, this will start to take over. So there are options for doing that, and we're definitely looking into that.
So is this the ECS new feature?
No, this is regarding Akka cluster.
Oh, Akka.
Yeah. So this needs to be done at like the application level to enforce the consistency boundaries. Yeah.
All right. Thank you.
Thank you.
All right. Take a short break and we'll be back with